Hi everyone, let's continue with this example about the function that gives the height of a ball after t seconds. So we've worked our way up to now finding a simplified expression for the average velocity on the interval 2 to 2 plus h. So this is starting at 2 seconds and going for h seconds after that, and then taking the average rate of change. And we're going to do this in a general way so that what we end up with is a formula that if you tell it how long your time interval is, it will tell you the average velocity from t equals 2 to t equals 2 plus your time interval. Okay, so we know that to find the average velocity, we're going to need to do an s of 2 plus h minus s of 2 all over h. And remember our function, here I'll sneak it in up at the top, was s of t equals 64 minus 16t minus 1 squared. So when we plug in a 2 plus h, we're going to get 64 minus 16 times 2 plus h minus 1 squared. And when we plug in 2, we're going to get 64 minus 16 times 2 minus 1, which is just 1 squared. So it's actually just going to be that 64 minus 16. And this all needs to be divided by h. Oh, and I maybe got a little bit ahead of myself here. I just jumped right to that h because I know where I'm headed. But really what happened was we had a 2 plus h minus a 2. And that left us with the h. Okay, so let's start simplifying. For one thing, I can see that this, let's see, maybe green will show up. Well, 64 minus a 64 is going to go away, so I'm just going to go ahead and do that to save myself a little writing. And I can also see that 2 plus h minus 1 is the same thing as 1 plus h. And then minus a negative 16 will be plus 16. Again, my biggest warning on these is watch the distributing negative signs. If things don't work out nicely, and by nicely I mean you get to cancel an h out of the bottom, top and bottom, but the bottom is the one that's giving us trouble, then go check and make sure you didn't switch a sign somewhere. Okay. So now I can FOIL out the 1 plus h squared, and I'll get 1 plus 2h plus h squared. Okay, and then I distribute the negative 16, so I have negative 16 minus 32h minus 16h squared plus 16 all over h. This is a nice thing with quadratic or cubic functions, is it can get a little tedious multiplying some things out, but generally you don't have to do a lot of massive fraction work or radical work. That's kind of convenient. Okay, so now the 16s are going to go, and I'm left with this negative 32h minus 16h squared, and that's fabulous because I'm able to factor an h out of that, which I will then cancel. So I'm going to go ahead and factor the h out. Again, if you'd like to, you can factor out a negative 16 as well, but it's canceling the h that's really key, so it doesn't really matter. Minus 16h. Okay, and then the h's cancel out, and my final simplified version of this expression is negative 32 minus 16h. Okay, so again, what I've just done is create an average velocity function. If I tell it how long my time interval is, it will tell me the average velocity starting from 2 seconds and using that time interval. So if I want to use this function that I just created to find my average velocity from 2 to 2.5, what I really need to do is compare this 2 to 2.5 with this 2 to 2 plus h, and recognize that my time interval, my h, is 2.5. So, I'm sorry, it's 0.5, not 2.5. Okay, so we need to plug 0.5 in for h, which means we get negative 32 minus 16 times 0.5. Half of 16 is 8, so I'm looking at negative 32 minus 8, which is a negative 40. So that's how this function works. You pick the length of your time interval, and it tells you, and let's go ahead and even put units on this, the average velocity over a time interval starting that long, starting at 2 seconds. Okay, and then, oh, shoot, sorry for a little bit of off the page. Bad about that so far. We are supposed to look back at our answer, and I'm going to disagree with my own self. I don't want to use the result of I want to use the result of h. So looking all the way back up here, I've said this is my average velocity function, starting at 2 seconds and going 8 seconds after that. If I want to change from average velocity to instantaneous velocity, again, we've been looking at the picture and working up to this. Hopefully you're seeing that what you would do is you would let h get smaller and smaller and smaller, and the slopes of the secant lines that you're getting would approach the slope of the tangent line. And remember that if your function is a velocity function, then those slopes, if your function is a position function, then those slopes represent velocities. So we want to let h get really close to 0. So we want to let h approach 0. And if we look back up at our average velocity function, if h approaches 0, the instantaneous velocity approaches negative 32. And we can even check on our calculator. I think I still have this thing in. If we want to calculate dy dx at x equals 2, there it is, negative 32. So we were right. This is working for us, according to our calculator. Use your result. Oh, I think I'm not quite following my own directions, but I've still said what I wanted to. I think I got one problem ahead of myself here. So as h gets smaller and smaller and smaller, we get that our instantaneous velocity is negative 32 feet per second. Okay, so basically this is our method. If we want the slope of a tangent line, or if we want an instantaneous rate of change of any sort, velocity is the only example we've worked on so far, what we need to do is write an average rate of change function with the length of the time interval as our variable, and then try to figure out what happens as the length of our time interval gets shorter and shorter and shorter. That's our strategy. So basically where we're at is we're doing almost all of the work for finding derivatives. Average rates are instantaneous rates of change. But we need to work a little bit on just some of the notation and the rules and the tricks that go with letting something approach 0 or anything. Basically, we need limits. This is where we're at. Limits are what allows us to talk about as h gets really, really close to 0, but isn't actually 0, what happens? Or as h gets really, really big, what happens? So that will be our next section. That's where we're headed. So we've laid all the groundwork for derivatives, and we just need to take one little sidetrack and make sure we're really solid with limits, which are also useful in a lot of other places. And then we'll come back and finish off this whole idea of calculating derivatives, instantaneous rates of change. Thanks for watching.